Good morning, everybody. So today let us start with Module 1. So in Module 1, let's begin with clippers and clampers. So that being Part A. Okay. Now, before understanding clippers and clampers, let us first try to understand the diode equivalent circuit. So what I have drawn is ideal diode model, right? Okay, so this is the symbol of a diode. So first let us try to build the ideal diode model. So in case of ideal diode model, what we assume is that the diode dynamic resistance RD is equal to 0. That means to say there is no ohmic resistance. And the barrier potential, which is material specific, is also equals to 0 volts. Okay. So Vk, as I mentioned, that it is material specific. For a silicon PN junction diode, the value of Vk going to be Vk is equal to 0.7 volt under room temperature, and for a germanium it is 0.3 volts, and for a gallium arsenide material is going to be 1.2 volts. Okay, so these are the practical values of Vk, which depends on the type of material used. On the other hand, in case of ideal diode model, we will not be worrying about all these values. We will just consider Vk is equal to 0 volts. Okay. So that being said, we can now construct the ideal diode model. So in case of ideal diode model, we are going to provide two separate circuits, one for forward biasing and one for reverse biasing. So first let us consider for forward bias. So what do you mean by forward bias? So in case of forward bias, what we do is the anode terminal of the diode is connected to positive terminal of the biasing voltage. And the negative terminal is connected to the cathode terminal. We will also consider a current limiting resistor R. Okay, so positive is connected to anode and negative is connected to cathode. So this is called as forward biasing. So we have assumed that the diode dynamic resistance is 0 and the barrier potential is 0 volt. So during forward biasing condition, diode acts like a short circuit. And equivalent circuit under this condition going to be something like this. So this is your actual device symbol, anode and cathode, and the equivalent circuit in this case is just a short circuit. So this is your anode terminal and this is your cathode terminal. So that means to say the moment you connect an external power supply to a PN junction diode, the diode gets into conduction, and this is your forward current, IF. So this is your forward bias equivalent circuit. So whenever we come across a diode symbol under ideal diode model, what we are going to do is we are going to replace the diode symbol with a short circuit of this kind. Alright. Now let us look at the reverse bias model. So in case of reverse biasing, what we do is we are going to connect the anode terminal of the diode to the negative terminal of the battery, and the cathode terminal is connected to the positive terminal. and resistor R is nothing but the current limiting resistor. Now, in this case, the following assumptions are made. The reverse resistance RR is considered as infinite ohms. That means to say, under reverse biasing condition, the diode acts like an open switch. Open switch is analogous to infinite resistance case. Okay. So during reverse biasing condition, the equivalent circuit of the diode looks something like this. So there is no interaction between anode and cathode terminal. So this is your anode terminal and this is your cathode terminal. So this is analogous to open switch condition, which is also called as open circuit condition. Open circuit condition. Okay. So summary. So whenever we come across a clipper circuit or clamper circuit, and if at all we have been asked to analyze clipper and clamper circuit on the basis of ideal diode model, then what you have to do is, if you come across a diode symbol, you replace the diode symbol with a short circuit. This is for forward biasing mode. On the other hand, if at all you come across the reverse biasing situation, we are going to replace the diode symbol with an open switch. This is for reverse biasing condition. Reverse biasing condition. So apart from ideal diode analysis, we will also be asked to do the analysis on a practical diode. So let us also look at practical diode model. So in case of practical diode model, whatever we had neglected in the ideal diode model case are accounted over here. So that means to say, the dynamic resistance is considered. So every p-n junction diode will have a finite dynamic resistance, which usually varies in terms of say some 3 ohms to 10 ohms. It's a very small resistance. Okay, and every p-n junction diode is made up of semiconductor material. It could be silicon, germanium, or gallium arsenide. So you will have some Vk value. If you use silicon, the Vk going to be 0.7 volt. If you use germanium, the Vk value going to be 0.3 volts. Okay, so if we consider Rd and if we consider Vk in our diode model, then the resultant diode model is called as practical diode model, or you can also call it as realistic diode model. Okay, but for the sake of simplicity, we don't regularly use the exact practical diode model. What we use is a kind of a derived model, which is called as first approximation. First approximation. So in case of first approximation, what we do is we first consider the practical diode model specifications, and then we try to derive the first approximation model. Okay, so what we do is, as you can clearly observe, that the dynamic resistance is quite small. Generally it varies from 3 ohms to 10 ohms. So for the sake of analysis, this dynamic resistance can be neglected. So we can assume Rd is equal to 0 ohm. And on the what basis we are neglecting this? The dynamic resistance is quite small, hence we are assuming Rd is equal to 0 ohm. However, Vk we are going to consider. Okay, either 0.7 volts if in case silicon material is given, or 0.3 volts in case if germanium material is given. Okay, so in our first approximation model, what we are going to do is we are going to just consider Vk. Now, as you can see, Vk is having a fixed voltage, 0.7 volts or 0.3 volts. So that's the reason this Vk can be considered as a DC source. Okay, why DC source? Because the potential remains the same. So with respect to time, the magnitude of the voltage is remaining constant. So Vk can be considered as a DC source. And also you must remember that Vk is barrier potential, and the function of barrier potential is to oppose the diode conduction. So Vk always opposes diode conduction. Okay, so you have to place Vk in such a way that it always opposes the diode conduction. Okay, so let us try to build a model. So let us try to build the first approximation diode model. So this is your diode symbol as usual. This is anode and this is cathode. And we are trying to insert the first approximation elements. Okay, so what we do is we redraw the diode symbol with anode and cathode terminal, and we are going to consider this diode as an ideal diode. Along with the ideal diode, we are going to insert the barrier potential. So as I mentioned, the property of barrier potential is to oppose the diode conduction, right? So you have to place the barrier potential in such a way that the barrier potential always opposes the diode conduction. So how do we do that? So you have the cathode terminal over here. So in order to respect the property of barrier potential, the cathode terminal should be connected to the positive terminal of Vk, and the negative terminal we are going to connect it to the power supply voltage. Of course, we will connect one current limiting resistor R, and this anode is connected to positive terminal of biasing voltage. So let's write V bias. V bias. Okay. So this is your first approximate model. First approximate model. So whenever we come across practical diode based analysis, what we are going to do is we are going to replace the diode symbol with this equivalent circuit. Okay. So this is for forward biasing mode. On the other hand, for reverse biasing mode, we can still consider the reverse resistance as infinity ohm, and so under reverse biasing condition, you can still consider diode as an open switch. Open switch. Okay. So summary, in case of practical diode model, we are going to replace the diode symbol with this equivalent circuit. So this equivalent circuit is consisting of an ideal diode in series with the barrier potential. You have to concentrate on putting the polarities over here. For example, Vk has to be put in such a way that Vk always opposes the diode conduction, and that's the reason we have connected the positive terminal of Vk to the cathode terminal. So now let us get into the clipper circuits. So first let us take the definition. So clippers are nothing but wave shaping circuits. Using clippers, we will be able to shape the the incoming signal. That means to say, if you want to remove a certain portion of positive half cycle, then you can use a clipper. Similarly, you can use a clipper to shape the negative half cycle of the input signal. So broadly, you can call clippers as wave shaping circuits. Okay, sometimes they are also called as slicers. Okay, slicers as in it is going to slice the waveform. Okay. Classification. Okay. You can have two levels of classification. The first classification is on the basis of biasing voltage. Biasing voltage. So, if an additional DC source is used in a clipping circuit, then we call it as a biased clipping circuit. And if there is no DC source used in a clipping circuit, then it is called as unbiased circuit. So, with a DC source in place, we are going to get a biased clipper. On the other hand, if you don't use a DC source, if no DC source is used, then we call it as unbiased clipper. Unbiased clipper. Okay. So, on the basis of biasing voltage, you can have two types. A biased clipper and an unbiased clipper. Biased clipper will have a DC source in the circuit, and in case of unbiased clipper, you're not going to have any DC source. Okay. Now, whether it is a biased clipper or unbiased clipper, you can have two types. Positive clipper and a negative clipper. Positive clipper or negative clipper. Okay. So you can have a positive clipper in biased clipper category. You can also have a positive clipper in an unbiased clipper category as well. Okay. So what do you mean by positive clipper? As the name suggests, positive clipper shapes the positive half cycle of the input waveform. On the other hand, the negative clipper shapes or trims or clips the negative half cycle of the input waveform. So this is the broad classification of clipper circuits. Since we have discussed about the types of clippers, now we can look into some of the clipping circuits. So first let us consider series clipping. So obviously when you have a series clipper, you are going to have a parallel clipper itself. So here itself, let me talk about parallel clipper orientation. So what do you mean by series clipper? In case of series clipper, diode comes in series with the load. And load we will generally consider it as Rn. So in case of series clipper, diode comes in series with the load. On the other hand, in case of parallel clipper, diode is placed across the load. So this is the difference. Example for series clipper is half wave rectifier. Example for series clipper is half wave rectifier. So let me just draw the circuit for series clipper as well as parallel clipper. The analysis part sometime later we will come. So you all know the half wave rectifier circuit. So this is the AC source Vs, which is connected to a PN junction diode, and this is cathode. And this is your load resistor Rn. Across this load resistor, we'll be measuring the output voltage. Okay. So as I was mentioning, that in case of series clipper, you can clearly observe that diode is traced in a series path. So diode comes in series with the load resistor. Okay. Now let us look at the parallel clipper orientation. Source voltage. So in case of parallel clipper, we are going to use a current limiting resistor. Let's write R limit, and then we are going to have the diode. So anode terminal and cathode terminal. And across the diode, you will find the load resistor. R. And across the load, output voltage is measured. Okay. So side by side comparison you can do. Here the diode comes in series with the load resistor. On the other hand, in case of parallel clipper, the diode is connected across the load resistor. Okay, so this is the difference between a parallel clipper and a series clipper. So we'll talk about the parallel clipper analysis sometime later. Okay, so let's start with series clipper analysis. So first let us consider a negative clipper. So example for a series negative clipper going to be your half-wave rectifier circuit. Source voltage, which is a sinusoidal source voltage. Anode terminal and cathode terminal. Okay. And across the load resistor, output is measured. Okay. So this is how the output is measured. The upper side will consider it as positive terminal, and the lower side will consider it as a lower potential terminal. Okay. Now, since we are carrying out the analysis, and in the beginning, as I mentioned, that analysis can be carried in two different ways, on ideal diode basis and on practical diode basis. So for this particular case, let's begin the analysis with an ideal diode model. So first let us consider ideal diode. What if you have been given with an ideal diode, and what kind of waveform you are going to get if at all you assume that the given PN junction diode is ideal in nature. Okay, so since it's a bidirectional signal, Vs is a bidirectional signal, so what you have to do is you have to follow some general steps. First you have to consider the analysis for positive half cycle of the input, and then you have to consider analysis for the negative half cycle of the input. So first let us consider positive half cycle of the input. What will happen during the positive half cycle of the input? So for positive half cycle, let us put the polarity for the source in this manner. So this is your source voltage. So for positive half cycle, let us consider upper side is at higher potential and the lower side is at lower side of the source is having minus terminal. And then comes the diode, and then comes the load resistor. And this is your output voltage. Analysis. So as you can see that during positive half cycle, upper side of Vs assumes positive polarity and lower side of Vs assumes negative polarity. And if we look at the diode working, you can clearly observe that whenever the positive terminal of the source is connected to anode, we say the diode is forward biased. So for the positive half cycle, diode gets forward biased. Okay. So in case of ideal diode model, whenever the diode gets forward biased, we are going to replace the diode symbol with a short circuit. So this is your anode and this is your cathode. Source, load. Output voltage with the given polarity sets. Okay. And if you apply KVL in this closed path, KVL in this closed path, you will be tracing the two potentials, source voltage Vs and load voltage V0, which is equal to 0. So this leads to the conclusion that your output voltage is nothing but the source voltage. And you have given the positive half cycle, right? So in case of positive half cycle, your output voltage is nothing but the source voltage, which is nothing but positive half cycle. Positive half cycle. So your output is the replica of positive half cycle of the input. Okay, let us draw the waveform later. Alright, so now let us look into the negative half cycle. So in case of negative half cycle, what happens is that the polarity of the source is going to get changed. So in case of negative half cycle, upper side of the source attains negative polarity and lower side of the source attains positive polarity, because your source is a bidirectional one. In every half cycle, the polarity changes. Okay, and this is your diode, anode, cathode, load resistor. Alright, so in case of negative half cycle, as you can clearly observe that the negative terminal of the source is connected to anode terminal of the diode. So when we connect negative terminal to the anode, we would say the diode is reverse biased. So during negative half cycle, diode gets reverse biased. And what are we going to do when the diode gets reverse biased? We're going to replace the diode symbol with an open circuit equivalent. So between anode and cathode, now there is no interaction. So it is as good as open switch or open circuit. Source, load, and this is your output voltage V0, right? So as you can observe that there is an open circuit in this case. So in case of open circuit, current is 0 amperes. And what is voltage? Voltage is nothing but I into load resistance, right? So current is 0. So it is 0 into RL, which is equal to 0 volts. So your output voltage during negative half cycle is 0 volts. So what do you mean by 0 volt? That means to say your output is clipped at 0 volt level. So entire negative half cycle is clipped at 0 volt level. So let's draw the waveforms here. Okay, let me write waveforms. X-axis is the time axis and y-axis is the voltage axis. Okay, let us separately plot input and output voltages. So right below the input voltage, you draw one more graph which talks about the output voltage. Okay, so input voltage is a bidirectional signal, a sinusoidal signal we have considered. But remember one thing, it need not be sinusoidal. You can have other forms of alternating signal. That is, you can even consider a triangular signal or a square signal. Okay, just for sake of simplicity, we have considered a sinusoidal signal. You can in fact even consider a triangular signal as well. All right, so let us look at the positive half cycle case. So in case of positive half cycle, what did we get the output voltage as? We have got the output voltage as V0 is equal to Vi. That means to say the output voltage during positive half cycle is nothing but the positive half cycle of the input. When your input attains maximum value, your output attains maximum value as well. Okay. On the other hand, during negative half cycle, that is during this case, the diode is going to get reverse biased, and due to which the output became 0 volt. So during negative half cycle, the output stayed at 0 volt level. So that means to say you have shaped the negative half cycle of the input signal, and that's why this particular clipper is called as a negative clipper. So you can write, we have shaped the negative half cycle, hence it is called as a negative clipper. So after writing the input and output waveform, we can also draw the transfer characteristics. So to draw the transfer characteristics, we will project the input voltage along x-axis and the output voltage along y-axis. Okay. So first quadrant is for positive Vi, positive V0. Second quadrant is for negative Vi and positive V0. Third quadrant minus Vi, minus V0, and fourth quadrant plus Vi minus V0. So to sketch the transfer characteristics, what we have to do is we have to find the slope m. So slope is calculated as, m is equal to y by x, right? So mathematically it is, delta y by delta x. Okay, so this is your y-axis, right? Output is projected along y-axis and input is projected along x-axis. So a small change in y variable, which is nothing but delta V0. So delta y corresponds to delta V0, and along x we have projected Vi. So a small change in x variable corresponds to delta Vi. So if we take the ratio delta V0 by delta Vi, we are going to get the slope. Okay. So you need to calculate the slope for positive half cycle as well as negative half cycle, and details of positive half cycle and negative half cycle we have already discussed. Okay. So let me write positive half cycle. So what did we get in case of positive half cycle? So we have seen that in case of positive half cycle, your output voltage is equal to input voltage. So what will happen to slope? M is equal to delta V0 by delta Vi. So your output is equal to input. So you can write delta Vi by delta Vi, which is equal to 1. So for the positive half cycle, slope is 1. And for negative half cycle, you can recollect the results. So we have obtained V0 is equal to 0, and therefore M is equal to delta V0 divided by delta Vi. So output is 0, so it is 0 divided by delta Vi is equal to 0. So in case of negative half cycle, we get 0 slope. So now let us place these details in the transfer characteristics. So what do you mean by one slope? So one slope corresponds to straight line with an inclination angle of 45 degrees. So that means to say, when your input reaches plus Vm, your output reaches plus Vm as well. Let me show you in the waveform. So this is what I was saying. So during positive half cycle, when your input is at 0, the output is at 0. When your input reaches positive maximum, your output reaches the positive maximum as well. So this is nothing but a straight line. On the other hand, in case of negative half cycle, the output is 0, and due to which you get slope is equal to 0. So in this case, you have to draw a line overlapping the negative x-axis, and this is the upper limit minus Vm. So minus Vm stands for the maximum value of the input voltage in the negative direction. So this is minus Vm. Okay, so the summary is that whenever you get AC output, the slope going to be an inclined line. On the other hand, whenever we get DC output, for example, V0 is equal to 0, so you can consider it as it's a 0 volt DC. So you are always going to get a straight line. Since it is a 0 volt, you are getting a straight line parallel to the x-axis, and in fact it is overlapping the negative x-axis as well. Okay, so this is the analysis of negative clipper on the basis of ideal diode model.